Hello, everyone, and welcome to the second session of Entanglement, Physics, Mind, and Worlds. I'm James P. Barbieri. For those who didn't see me yesterday, I'm the program coordinator here at the Party Center, and I'll be host for the next few weeks with you. I'm here to help you throughout the call. So if you have any issues, feel free to just let me know in the chat. Just very briefly, just a few reminders to please keep your microphones muted. We do encourage you all to keep your cameras on. The chat and captions are open for your convenience. And of course, feel free to use the chat to talk to everyone in the group. And that this session, of course, is recorded for archival purposes, and you should receive the recording for the session in a few days. So today we have the honor to have Professor José Ignacio Latorre to lead the session. José got his PhD in particle physics at the University of Barcelona. He was a Fullbright Fellow at MIT and a postdoc at the Niels Bohr Institute in Copenhagen. He then became associate professor at the University of Barcelona and later full professor in theoretical physics. He has written over 100 papers on particle physics and quantum information and has directed 12 PhD theses. He produced 2 documentaries, one of them on the last voice of the Manhattan Project. He is a founder of the Centro de Ciencias de Benasque, Pedro, Pascual, and was a founder of the NNPDF collaboration and partner at the Entanglement Partners. And with that, I'll pass it over to you. Welcome.
So thank you very much, James, also Alex, and definitely also Eleanor. So let me first share my screen, if okay. Here it is. Okay. Can you see it, James?
Yes.
Yeah? Okay, thank you very much. Okay. So thank you very much. It's a real pleasure. It's not the first time, Alex, I've collaborated with Alex. It's a pleasure always to do things which are not at all obvious, just talking across fields. And in particular, because the subject of entanglement is such a challenge. Okay, it is a non-trivial challenge, definitely. First, let me mention, just to complete what James said, that I quitted my position in Barcelona, my full professorship, and I moved to 2 centers. One is in Singapore, and where I'm directing the Center for Quantum Technologies, and also in Abu Dhabi, there is an effort to create, for the first time, a top-level center in quantum in the Emirates. So actually today I'm talking to you from Abu Dhabi. So entanglement, I understand that yesterday Jonathan went, and it was very nice, as I learned, to a presentation of entanglement. I guess that you would get as many different presentations about entanglement as speakers you could find. It's such a rich subject. So what I found is maybe reconsider what I said in the beginning, that we'll talk entanglement for quantum computation. And rather, I will go a little bit more philosophical and, you know, trying to be very, very introductory in some way. But towards the real efforts that we are doing nowadays, which is building a quantum computer. Okay. So let me go ahead. You may know, I've chosen this picture for entanglement. I guess that you may know that the word entanglement was introduced in 1935 by Erwin Schrödinger in a paper to answer a criticism by Einstein, Podolsky, and Rosen to quantum mechanics. And the way he managed to tell why it was such a non-obvious result, what they were discussing, and why there were some correlations between 2 particles, he chose that cannot be disentangled. He chose this idea of the cross arms. Okay, so actually, to be more precise, okay, the paper of 1935, he used the words, I cannot pronounce it. Is there any German in the audience? Beschränkung? I don't know how to pronounce it. By the way, it is my...
Shrink.
Could you say that louder?
Shrink.
Okay. Wow.
Wrinkle.
Yeah. Actually, it was Schrödinger himself who translated it to English, to entanglement. So this choice of word was done by Schrödinger. And then, because I'm Spanish, I wrote it in Spanish and then in French, enchevêtrement, implication, and even in Japanese. So the basic idea is something you cannot disentangle. And as you will see, it's related to how particles can be correlated. This is the deep idea behind. So let me go ahead. So my first statement to understand where we are today is that this is not something that happened last year, okay? Neither in 35. So you have to go really back in time. And it's about quantum mechanics, really. This is what is at stake. What is the role of why quantum mechanics is so different from classical mechanics. And to do it, I just wanted to mention, to give one example, okay? So I will do it by first discussing a little bit where are we in the 21st century if you think in quantitative science. Well, the very first observation is that quantitative science is a baby. Okay, it's only our first solid equations come from Newton, okay, where we do have postulates and very clear equations that allow us to do all the engineering, everything. It comes from the second half of the 17th century. So actually, it's in the first half of the 17th century where René Descartes establishes this idea that one should look for the what you would call, well, reductionism. You have to reduce what you don't understand to the bare minimum. You have to identify exactly what you cannot deduce from something else. So this idea, this rationalism that starts with Descartes, proved to be very, very successful in science. And not only that, but Descartes also introduced a method, how to proceed to accumulate knowledge on top of the previous knowledge. So it reduced the rationalism in all possible ways that we relate nowadays to science, in the way of isolating what is not understood and in proceeding from that to more complicated knowledge. So by exploring the parts and only putting them together in the end. So it followed a century of success of the ideas by Newton, and this, you can call it a mechanicism. 18th century was very, very successful in these terms. And also, you may think that the 19th century was a century of chemistry, the big progress of chemistry in the 19th century. In the 20th century, definitely in the beginning, we had quantum mechanics and relativity, and also biology of the 20th century. And if I had to choose a word for the beginning of the 21st century, I would call it information theory, which includes many things, but in particular, artificial intelligence, neural networks, and definitely quantum information. Everything is about re-understanding our knowledge in terms of information. I hope that the second half of the 21st century will be the time of ethics. This is my particular dream, because I belong to the committees for advising on ethics and artificial intelligence of the government in my country. And well, there is a non-trivial path that we have to go through. But if you look at this, first science with equations, real equations, so differential equations that we can integrate, it's a baby. It's only 300 years old. Okay, and but on the other hand, it's amazing. No, it's you get the feeling that the acquisition of knowledge is unstoppable. It's inexorable. It's not a matter of opinion. And we simply will get very far, extremely. Okay. All these ideas that we live in an acceleration, times of acceleration. I do think that it has been so for many, many millennia, but the feeling is that we are getting there very fast. I will try to argue where are we heading at later on. So I insist on the quantitative science. So why let me be one example to make it more clear. You know, when I was in high school, I attended the French school, the Lycée Français, and we had plenty of hours of philosophy and Greek and all sorts of discussions there. So I remember very clearly when my teachers taught me the aporia of Zeno of Elea, the philosopher from the Magna Greece. Okay, and the idea of Zeno was that you know, here you have Achilles, run, or an athlete, and just to get to the target, he argued this athlete should cover half of the path, okay, to get half of it. But of course, before getting to half, he should get to 1/4, half of the half. And before 1/4, 1/8, and so on. And this chain goes up to infinity. And he argued that therefore the athlete could not move, okay? There would be no motion. And this, at that time, okay, was a dispute between philosophers. And you may argue that this is the idea of not being is not, okay? So the change is not, so you don't move. And this is how the philosopher would discuss, and then you would have the opposite, no, the being is and the not being is not, and all the dispute and Parmenides and all these people around. So, and you can debate. There is a little discussion on this paradox by the writer Borges, the Argentinian writer, and you see the mess he's in. Yet, if you introduce equations, suddenly all these things are understood much easier. So let me take it back and let me take for serious Zeno's argument. Indeed, this athlete must run from 0 to 1, and before that, call it d, the distance d. But before that, he has to go to distance d half, and before that, he has to go to distance d/4, and so on. So let me reproduce his argument. Okay, and this carries to infinity. Well, what he doesn't say is that you also need time. And when you take the time to go to d, you need t. When you go to d halves, you need t halves. When you go to d4, you need t/4. So the time divided by 4. And when you take the equation, which is something that was not there, okay, in the time of the Greeks, you take d/t, and then d halves over t halves, the 2 and the 2 cancel, the 4 and the 4 cancel. You have that all of them are equal, and this is what you would call the velocity. So the motion exists because there is velocity. Okay? And this is the precise way of doing that. And now I can predict. You tell me whatever distance you want to go, I simply would take t, I pass on the other side, and I would tell you the time. Okay? I would deduce the time. So that's the difference between discussion.
Speak up a bit.
Yeah?
Would you mind being a bit louder? Speak up a bit.
Oh, if you cannot hear me, I will move to this other thing. Hold on.
Thank you.
What about now, James?
I think that's much better. Yes, thank you.
For sure.
Yeah, I can. Yeah, much better.
Much better. Okay. I think none of them work. Just say again, much better.
No, I hear you much better compared to earlier, but yeah, thank you.
Okay. So I'm not going to use equations a lot, but I wrote one so that you understand the contribution of Newton. So what Newton did is to formalize this as little increments. And he said that actually, if I take this to infinity, it would be that the increment I travel divided by the increment in time is constant. And it's a limit. And this is what we call calculus. So Newton, and indeed this notation is due to Leibniz, come in this period. And from then on, we do have an equation that perfectly describes this. So what Newton did, and this is the amazing step, is that he found the equation that really controls the motion of objects. He wrote that in 1686. Although his work, he was in his mid-40s, his work is when he was on his 20s. It took the effort of Halley to produce the first edition of the Principia. And the reason was that he was missing one computation. It just happened that he managed to get the computation done. It is what is the effect of the spherical mass on a point, an external point. He managed to do that in 85, and then in 86, everything was written. By writing that any force produces a universal reaction, which is an acceleration, okay, and that the constant, the obstruction to accelerate is mass, the inertia. He wrote the equation that simply describes the reaction on every particle. Whatever the force, the nature of the force is, the reaction of the particle is universal. It's the same. It's simply, it accelerates. You may have tons of forces on a particle. The reaction is that it will accelerate. And therefore, I can now write this equation in more detail, establishing which force I want, and I can, what we call, integrate the equation, and we describe with full glory the result of that motion. So we have become quantitative. And this is the beginning of the age of precision. So as soon as you are quantitative and you have precision, you may, with full honesty, discard a false theory. You can falsify theories. So you claim that this is not the law of the universe, it's a different law. Okay, we solve it, and now we go to the experiment and we compare the two predictions. Given that both are so precise, it turns out that we do have a way to discard the wrong ideas. And this is critical. That's the beginning of the real progress of science, no? When you go into the detail, okay? It's not about the wishes. May I say that Newton wrote more than 20 versions of the inertia principle, and in the first version, he, rather than inertia, he was using the idea that the particles had a soul. Okay, it's by himself that he was evolving his concept till he got the idea of inertia. So this is fantastic, okay? All of our engineering, all our bridges, all our towers, all our machines obey Newton's law. And we have produced a very solid economy and technology out of that. Okay. It just happened, something unexpected by the end of the 19th century. At least that the Newton laws were perfectly okay, but there were some experiments that were not following precisely the laws that Newton had proposed. And these two situations were very, very special. So the first is related to high velocities. When the particles travel at high velocities, something didn't match. And the second, and in particular, you had the mismatch between how we understood light and matter. And you will see now why. And the second is that when we went to elementary particles, like photons and electrons, they didn't obey the very same laws. So there was something that didn't work. So you see, it's like pushing to the boundaries, the theory. So the bulk of the theory work, and it works today. If today you have to make a bridge, you rather use Newton's equation. It's simply that in some limits, this didn't work, okay? And here we go. The first conundrum was solved by Einstein, Albert Einstein, when he was a very young person, 1905, he was 26. And he was not a professional, let me say, academic at the time. He came with a profound idea that there is in nature a maximum velocity. You see, Newton's law, this is not the concept. I mean, you simply have a velocity and nobody says whether there is a limit or not. That's perfectly okay not to have a limit. But Einstein postulated, he could not prove it. It was like Descartes would say, a principle, a reduction of our unknown to the fact that if you postulated that there is a maximum velocity, things would match. And this velocity, he called it c. And c is the speed of light. So light is made of particles, which are called photons, and they travel at the maximum possible speed, which is the speed of light. Actually, all the interactions that typically we experience are mediated by light. And so when you have two electrons that get attracted or repel, what they are doing is an exchange of a photon. Therefore, light is the mediator of the interaction. So that means that if one particle has to influence another particle, it has to be done with light. And because light travels at the speed of light is the speed of causality. Causality be defined as an action that modifies the state of a second particle. So we cannot violate the speed of light. Nothing travels faster than light, and light precisely is causality. Okay, so this established an order in time, and precisely this theory was very, very difficult in the beginning to understand by many people, because the way your time runs, Einstein proved, depends on your state of motion. Okay, so if two bodies travel at different velocities, their relative clocks tick at different pace. So this was the non-trivial effect of the theory of relativity, and it was revolutionary at the time. Now we are more than a century after Einstein, and if we look back at what was the step that Einstein took, was really a remarkable step, but it is a natural extension of Newton physics, adding this phenomenon of keeping the velocity of light as a maximum and changing the addition of velocity. So even a guy that will come today later, which is John Bell, he used to teach special relativity at CERN. Well, he wrote a booklet. And there in the introduction, he says, well, many people say relativity is a revolution. I think it is not a revolution. I think it's a continuation of the knowledge that we had. Okay. Instead, the second problem, that is how the particles behave, the elementary particles, turned out to be dramatically more profound. So the first equation that needed a change, okay, a non-trivial change, was written by Max Planck, and we know in detail the anecdote. It happened on the afternoon of October 7th of 1900. He was in Berlin. He was the very well trained, highly educated family. He was about to become a conductor, orchestra conductor. He had perfect pitch. He was a conservative in many of his ideas and turned out to be a revolutionary in his science. So what he needed was to write an interpolation between two behaviors of the same phenomenon, which is the so-called black body radiation. And he couldn't match this equation unless he introduced something not new. And he had to introduce a constant. This constant, nowadays, we call it Planck constant. And it is written as H, and often H bar, with a little bar on top. That means H divided by 2 pi. And what is H bar? Is a fundamental new constant. Just like C was a new constant, the velocity of light, the maximum velocity of light is this C, a constant. So H bar was a fundamental new constant. And this is an action, energy times time. So it's like the energy and the time of a transaction. Call it an action. It is called action. Think of it as a transaction. So there is a minimum amount of action. So wow, the laws of physics have taught that Newton is just like a principle, but at the scale where Newton works, you don't see the high velocities, neither the very small objects, where finally there is something waiting for you. There is a minimum exchange of energy. And that has dramatic consequences. So now, a century after this, we can say that conceptually, quantum mechanics is an absolute revolution. It changes the language of physics, it changes the relation, the philosophical relation that we have with nature. So let me just be slightly more precise in the next few slides. But maybe I don't know, James, Jonathan, maybe if we may pause for a second to see if somebody would like to say something or dispute something or agree on something.
Yes, absolutely. Jonathan, did you want to add something?
Not at this point. Sorry to sound like a cop-out, but not at this point. No, I'm just looking at what's popping up. Lots of interesting comments in the chat. Perhaps I could mention something that Gary said, that Einstein was attempting to preserve Newtonian mechanics against the sort of the issues that were arising. What do you think of that thought?
Yeah, as I said, relativity is not a profound revolution as quantum mechanics. It's very conservative. It tries to keep all the language of Newtonian physics. Okay, so I agree with this comment. I mean, at the time there was quantum mechanics was not formulated. So in 1905. So the idea of protecting against other things was probably not there. But indeed, I agree that Einstein was, in this sense, preserving the essence and modifying it to the point that would accommodate for the new measurements. It is important to understand that the approach that Einstein had in that time is statistical physics. He was a very good statistician. Actually, all his major papers are in statistical physics. So he was really dealing with absolutely normal science and just making the rational extensions. It turned out that it was a surprising extension with amazing properties, you know, with the twin paradox, with things like that, that people were amazed. And it is true that after that, it took him another 10 years to produce the second part, which is the theory of general relativity, which is much more profound, okay, in the sense that there you absorb the gravity force as a deformation of the space-time. But the special relativity is a very moderate, small modification as compared to quantum mechanics. Quantum mechanics is really a dramatic disruption.
So would you agree with the thought that Einstein and perhaps Planck were among the last of the classical physicists rather than the first of the quantum generation.
Absolutely agree. So there are a number of examples to clarify that. You may know that once Einstein was looking for a job, he had a recommendation letter to Planck, and Planck said he was a brilliant guy, as it proved his theory of relativity, with a minor, he was a little bit out of the right path with all these ideas of quantum mechanics he was proposing. Okay,
yeah.
So the letter of recommendation was in the direction that the only bad thing that Einstein had done was actually the one that gave him the Nobel Prize, which is the photoelectric effect. Okay,
yeah,
very peculiar. Both of them, and more so Planck. He was even more conservative than Einstein, and yet the contribution of Planck is more disruptive. You know,
yeah.
you are put in situations in life which are very odd, no, very, very odd. But so let me go into this ahead with this philosophical thing. I will get to entanglement, no doubt about that. Okay, but I'm simply. I believe in building pyramids. I mean, in starting with peace, all the bases. Otherwise, what do you do there? So why is it so profoundly disruption? I would again. I did before. No, the mathematician adding mathematics to physics was. I gave the example of the Zeno effect, the Zeno paradox. So let me now take another experiment. Gedanken experiment, an imaginary experiment. And my experiment is very simple. I'm walking in the street and I see a red car. This is it. This is my experiment. Okay, I see a red car. And now I'm a philosopher. So I ask myself, what do I mean by I see a red car? Well, let me understand then, before what I mean, what happened. Then I realized that if it is, pitch dark night, and there is no light, I don't see even the color of the car, I don't see the car. So I realized that actually the very first element is that there is sun, and the sun is shining, and it shines on the car, and the light bounces to my eye. And then I realized that in my eye, there are some cells that capture that light. They are specialized. The cones, the peaks, they selectively collect light of different colors. And this goes to my optical nerve, and this goes eventually to the brain. And it is the brain that makes up the idea that I saw a car. But if I don't have the sun, the light bouncing on the car, I don't see anything. It's not my brain. It's just the very first fact is that this has to happen. And that brings the very idea that I have to probe the system. The light is probing the fact that the car is there. My probe, it's my message. It bounces from the car. So what really, really, really happens is that one photon left from the sun. There was some nuclear reaction. Something happened in the surface of the sun. The photon traveled, 150 million kilometers. It reached the Earth. It reached the car. It bounced from the car, and it came to my eye. Okay, this is what happened. And then suddenly, I think it's a collision. It's a collision what happened between a photon and a car. Indeed, it's a collision. And the photons are, they are particles without a mass. They carry some energy, but altogether, the light carries energy. Definitely, if you go under the sun, you will get burned. No? It does an action on your skin. No, so it carries energy, but it's a moderate amount of energy. And the car is a heavy car. So the inertia of the car is enormous, and the car simply receives the collision of the photons and stays parked in the street. Nothing happens to the car. Nothing serious. But now think that you send this light, and I picture a laser, to a single electron. And then it bounces. And I simply check. I get the photon bouncing back in a detector. But you see, now what do I say? There is an electron here? No way. Because the collision of the light with a single electron is superb. So the guy simply gets ejected in a dramatic way. So when I say here on the left, I see a car, the car is there. But when here on the right, I say, I see an electron, the electron is not there, okay? So actually the process of observing the electron has modified the electron. The electron is no longer what it was. This applies to any microscopic element. So I may have excited the electron, maybe the internal state of if it were an atom, the internal state of an atom would have changed. Maybe I produced dramatic changes in the structure of the object I'm observing. So the very point when I go to very small particles, elementary particles, is that the process of observing, the process of measuring changes what we observe. There is a change. And on top, the laws that later were fixed in quantum mechanics, it says that there is an uncontrollable change. You cannot predict it in full certainty, only in a probabilistic way. So all these changes everything. So what do we do? I mean, we don't know whether the electron was there. What can I write? Can I write an equation of motion? Can I write the velocity of the electron as it moves given a force? Well, I cannot do those things. So should I drop all the paradigm? Should I drop positions, velocities? Should I change everything? Are there fundamental limits? Is there what later was discovered, a Heisenberg's uncertainty principle that limits what we can know about an object? So in the very small, there is this profound change, which is that measuring affects the observed object. And we don't know how to handle with that. So let me summarize a little bit why this is the change of philosophy, okay, the course of philosophy. The very first thing is that we can only acquire limited knowledge, okay? Because we can refine dramatically where the position was, but then we change dramatically the velocity, or we could then not measure the position with great accuracy, and then the velocity would be controlled, but we can never have absolute knowledge. So the theory of quantum mechanics is a theory about how much knowledge we can acquire and manipulate. So it's not about what is an electron. This is not there. So you should say we drop all our efforts in ontology and we move to epistemology. So we are concerned about what little we can say in the world of the smallest. So this is the very first dramatic thing. The pursuit of absolute knowledge of absolute reality is no longer possible because we have this enormous fact. By the way, if I go back, the reason why I always modify the object is there is a minimum action of transaction. If it were not for this, this paradox, I could solve it. It's the fact that there is h bar that is limiting my. There is a minimum I should always affect the observed particle. The second, it's more for the practitioners. So if this is the case, at variance with classical physics, the measurement is part of the theory. So if you think carefully, in Newton, you never mentioned what is a measurement. You simply talk about space, velocities, time, and you give for granted that you can always measure everything. It's no obstruction. Whereas in quantum mechanics, this is an abstraction. So measurements is a postulate in quantum mechanics. How the effect of measurement. It's a postulate. And the third, it was discovered later, little by little, is that all these processes carry an element of genuine uncertainty, of genuine randomness. So that the discussion will drop the old ideas of determinism and also of free will. So quantum mechanics produces the third paradigm in this difficult problem. You know, determinism is that the laws of Newton are there for everything, so therefore everything is written. It was written the day of the Big Bang that today we would be here talking. It's written the day we will die, the day we will get in love, the day in 1,000 million years, whatever happens will happen. It is written because it's just the inexorable evolution of the equations of Newton. Okay, so this is determinism, scientific determinism. Free will is no. There is something which in nature is not only Newton equations and I decide. Although nobody has come up with why and where the departure from Newton's laws happens. They have been experiments on decision making, okay, on the brain, can predict with hundreds of milliseconds the decision you will make, which is in a way how you trigger the macroscopic reaction from microscopic changes. But there are schools of thought related to free will. Quantum mechanics says, no, the equation is not Newton, it's another equation, and on top you work with probabilities, and the moment you measure, you will have a probability realized, and therefore there is a genuine element of randomness. It is not determined, there is no free will in quantum mechanics, it is simply, there is an element of genuine randomness. Let me be clear. The evolution of the states is deterministic, follows the Schrödinger equation, but it's at the level of information. And when you measure, there is an element of randomness. So it's a complicated, very convoluted third way of understanding the same problem. So as you see, no doubt that many books have been written on the challenges posed by quantum mechanics. If you like philosophy, it brings a completely new discussion into the table. Okay. So let me then make it clear before going to the next step. There is a change of paradigm in quantum mechanics. We no longer, like in classical physics, we try to describe the position R of the particle at a given time, t, but rather you forget all that and you work with a new concept, which is something that relates to the probability of finding the particle at a given time in a given position. That's what you do. So you drop the hard description of positions, okay, to something which is, let me say, soft, more diffuse, no? Which is the probability of finding. We call that the wave function, and we write it with the letter psi, Greek letter psi. And please note that psi depends on the position and time. So psi depends on both of them, whereas in classical physics, the position depends on the time. Okay? If you follow your trajectory, after 10 seconds, you're in that place. This is classical physics. In an atom, you simply describe where the electron may be at a given time. Okay. and you change the evolution from Newton equation to Schrödinger equation. So now you see the difference. No, in relativity, we still manage positions, velocities, forces, and the way you combine them was changed to accommodate for a maximum velocity. So it was within the same scheme, the modification that would make sense to have a maximum speed. Whereas in quantum mechanics, you change the language of physics. You change the way you describe things. Okay. So maybe again, Jonathan, maybe this is a point to reflect a little bit.
I was just about to type an answer to a question that has cropped up, but seeing as you stopped, let's bring it to the table as a discussion. We've been asked, what is it about measurements that affects what is observed at the quantum level?
Mm-hmm. So it's a very hard question, depending on the level you go. I will give you the recipe in a while. What is the recipe in quantum mechanics we have to follow to make good predictions? But if you are here, we are at a little bit more philosophical level. Now, what is it? So the point is that a measurement is a relation between something which is very big, like a human, something which is very small, like an electron. So it's a very uneven relation between the macroscopic observer and the very tiny, okay, element you want to measure. So what happens is that all the bulky big detector alters the properties of the small particle in a defined way. And this is what the measurement does. It's a gigantic piece of matter acting on a very tiny piece of matter. And that produces a dramatic change on the small one. Okay? And the way it is done, we don't control. We cannot describe this path between the macroscopic 10 to the 23 particles to one particle. So we summarize in a rule of what is the effect. Okay. So today, as we speak, there are a number of teams in the planet that are trying to penetrate for the first time this barrier of understanding measurements in more detail as a sequence of more elementary actions that may be understood in a better way. But if you go to any class in any university, you will be taught a rule how to keep track of the probabilities in a given way, and that I will come just in the next section.
Thank you.
Okay.
Yep, I think that's good.
Okay. Let's move. So, in this new language, what happened is that it was a time of tremendous confusion. Since the year 1900 that Planck wrote his first equation, he was so sad with the found fact of introducing a new constant in nature that he didn't publish, neither wrote his idea to his colleagues in 2 months. So he took his ideas by the end of the year to a set of colleagues. He kept recheck. He checked 30 times that everything was correct, and then finally he accepted that the formula was good, and they discussed. The meaning of this was not at all clear, and there was many other experiments that not even with his formula was only for a particular experiment, but people took the idea that there was this unit of action, this h bar. So Einstein used it for the photoelectric effect, but also Bohr in 1913 described the atom, the levels of energy. There were people trying to accommodate things to the old classical physics, Sommerfeld, did, and there were 25 years of a complete mess. It was then in the winter of 25-26 that Erwin Schrödinger, on a vacation time, skiing resort, he solved his equation and described perfectly the atom for the very first time, all the levels of energy, everything with a precision that was flabbergasting to everybody. In 26, things seemed then changing, and there were a number of new contributions. And by the year 31 or 32, I don't remember now, it is von Neumann that writes the postulates of quantum mechanics as we teach them in many universities. So it took 30 years since the first equation to write down the postulates. So this is just, and these people were clever, okay? We are talking about Heisenberg, Schrödinger, Bohr. It was not at all trivial to accept what was the right framework for that. So when the thing was written, okay, let me now tell you a few of the things that contains the theory of quantum mechanics. And the first and tremendous one is the so-called superposition principle, okay? So again, I do it with an experiment. So Gedanken experiment. But this is so famous that nobody can complain. This is the double slit experiment, okay? So the idea is the following. We throw particles through a double slit and we detect them on the right. Well, in classical physics, it's very easy. The particle goes through one slit, it may have some interaction with the slit and then go and is found somewhere else. And we describe that. That's it. That's what happened. The particle went through the slit and was detected on the right. Okay? Well, quantum mechanics says that if the particle is detected on the right, it may happen that it went through the upper slit and was detected in that place on the right, or went through the bottom slit, but was found in the very same place on the right. So these are two paths that lead to the same observation. The particle is at that point on the right. Let me call that compatible histories with the observation. So we have one observation, which is the particle is in that place, but there are two histories, two paths, which are perfectly okay, compatible. So what quantum mechanics says is that the way we describe the amplitude of probability, the wave function, must account for both facts. So it's made as the addition of the first possibility and the second possibility. So quantum mechanics says simply, systematically, that this is how you should proceed. You are on the right, you don't know what happened. So it's an information you are missing. And there are possibilities. You simply, your wave function is the addition of all these possibilities. And this is the so-called superposition principle. Okay. Now, it is tempting to say that the particle, according to quantum mechanics, passed through the two slits, but it's not correct. Okay. Quantum mechanics never says about reality. It never says what is with precision. It says that only about probabilities. And it is giving us a bookkeeping rule. This is the way you should proceed. Okay. And now, don't be deterred by this picture. This is just to understand the experiment that was done. As you see on the left, I have a source of electrons. I throw them from a double slit, and I move the detector up and down. So I repeat this millions and millions of times, and I simply start to collect statistics. And here is the difference. If the world is classical, the particle goes through the slit 1, which is red, And you see in the middle, the P1 probability, which is a line, which is a Gaussian around the point where you detect it, most probably. If it goes through the slit 2, you see a blue line. So if you add both of them, you would have the addition of these two curves. That would be the classical work. If instead you do it in quantum mechanics and you first found the history, the probability is the square of the wave function. Then it turns out that these histories, which are waves, they have interference, they cancel sometimes, like our waves in the sea. And then the pattern of interference is what you see in this purple line. So you see, in quantum mechanics, it's telling you that the particle obeys the law as if it were a wave, okay? Hence the name wave function, okay? That's the origin of the idea of a wave function. But this is exactly what we need. An experiment that can discriminate between possibility 1, classical physics, or possibility 2, quantum mechanics. So we simply go and we do the experiment. Okay, that's what we need to do. So may I change my, momentarily, I will go out and I will show you an experiment, real experiment done with that, okay? So that you can check whether the world is classical or quantum. I go out and I need to share again, but now I have to share this. Can you see my screen now? Yeah, it's a black screen. So this is 2 slits which are vertical, and this is a real experiment. And now every time you see a white dot is where the particle landed. You may remember, if the wall is classical, you would have a continuous of points. If the wall is quantum, you will see these interferences. And let's do it with electrons. This is not with particles. And you see, now we will discover whether they behave like particles or like waves. So you see the interference pattern. So the world is quantum. Okay, it's the electrons have interfered as if they were waves, not as if they were Newtonian particles. Okay, so again, let me go back to Zeno. This is why we make progress, because we have these perfect equations that can discriminate between 2 predictions. And the prediction in quantum mechanics is interference with all these zeros of probability, whereas the other has no zeros. If you find zeros of probability, classical mechanics is not correct, and quantum mechanics is correct. This is one of the very many experiments. It was done in 1928, and the first time that it was done with electrons. And it has been done, amazingly enough, in the recent years. People want to send through the double slit bigger and bigger objects. So later it was done with neutrons, the second half of the 20th century. But then it was done with nucleus of atoms. And in the beginning of this century, it was done with fullerenes, so carbon 60 atoms of carbon making a ball. And this is it has 720 nucleons. Okay, this is a gigantic ball. You throw to the double slit, and you see the perfect interference. So each ball has a 720 nucleons, is interfering with other paths that the ball could have taken. So this is the idea of trying to see macroscopic effects related to quantum mechanics. Very, very impressive. Okay.
Can I just make a comment?
Sure.
Do you mind if I just make a comment? Just, you know, some of the people in the audience may not be aware that Anton Zeilinger, one of the people that's just recently been awarded the Nobel, his group were doing some of the amazing experiments that you're just talking about. They've pushed the boundary higher and higher and higher. And I think I read somewhere that their ambition is to get it up to the level of a virus.
Yeah. They managed to get to a molecule related to photosynthesis, and this was 10 times bigger. So this was of the order of 6,000 nucleons. And they also saw the pattern. With viruses, as far as I know, it has not been done because on the left, you have to throw these particles.
Yeah.
So the way you do that is by hitting them in a chamber. Okay, they get velocity and then you throw them. And for the velocity to match the experiment, it turns out that the viruses get broken. So this is the problem. This is the problem you have, that the preparation of this experiment is very, very difficult with viruses. But it would be fantastic, no? A virus with a double slit. People would say the virus went through the 2 slits at the time, but as you understood, this is not the right way of saying. But it's amazing. Now, if you guys are wondering what is the largest object that shows the properties of quantum mechanics, no? In an obvious way, well, there is a debate for that, but definitely one of them could be a neutron star. Okay, because the neutron star does not collapse because of the Pauli.
Yeah.
Well, so it's a very gigantic object that is genuinely quantum. Okay, so let me reformulate once again the superposition principle. So it says that the information of a system is made by the superposition of all valid histories. Rather than using the psi of something, let me from now on call it this funny symbol, which is a vertical line and a bracket on the right, and psi is inside. This is called ket. This was a wave function, and this was introduced by Dirac. Okay. Dirac was a very funny guy, well, very funny. Let me moderate my comment. Was a peculiar guy, and he loved jokes, and he decided to call this ket because it's half of a bracket. Okay, you think of a bracket. This is half of it. Call it ket. So of course we call what we call the adjoint, which is on the other side, we call it a bra and a ket. Okay, so the ket. Why ket? Well, you could have put an arrow on top of it. You could have put a tilde. We could have any symbol that really reminds you that this object is a quantum object and obeys quantum equations. So it's a way to make it distinct from all the previous notation that you may have in nature. And written with Dirac notation, well, any state of a system may be a superposition of possibilities. Okay. Now, why is this so funny? Because you may consider superpositions that are striking to your ear, no? For instance, when we talk about spins, which are like little arrows in the magnetic field pointing in some direction, you may be in a superposition of pointing up and pointing down, or a superconducting current rotating clockwise or anti-clockwise on a superposition. Well, my information is compatible with both, so I carry them, okay? Or I'm here or I'm there, or I'm alive or I'm dead. So quantum mechanics has no problem with that. Your information is compatible with both things. There you are, you keep it, okay? And this gave a fantastic paradox that was proposed by, no, it was not a paradox, but again, this guy, also peculiar guy, Schrödinger, that he proposed in a paper this idea. So I do have, because I'm here. Again, I have to do it with PowerPoint, not with this, sorry. I will do it properly. This is I cannot do it yet. Just a second. Just a second. Sorry that I forgot that there are some small animation. Here I am. Okay. Where is the Schrödinger cat? And now I have to go back there and share. Didn't think of that. Okay. Wow. Again, can you see that? The cat?
Yep.
Okay. So the paradox by Schrödinger is the following. We have a box. And you have this mechanism on the right. This was described by Schrödinger. You see how careful he was on everything. On the top, you have a machine where a random event happens. And this event may be produced or triggered by the disintegration of an atom or something. So something genuinely random. And then if it happens, a hammer falls and it breaks a bottle full of poison. Actually, even he wrote that the poison was cyanidric acid. So he was very careful in setting up the Gedanken experiment. Okay. And here's the cat. So there are two possibilities. Either that random fact, this disintegration, does not take place and that the cat is alive, or it takes place and automatically the cat dies. Okay? So this is the situation. So imagine now that the box is broken. Okay, you left the cat inside, alive. You close the box, and after a while, you ask yourself, what is the right description according to quantum mechanics of the cat? Well, I don't know. In a possible history is that indeed the atom disintegrated and the cat is dead. The other is that it didn't disintegrate and the cat is alive. So the way to describe in quantum mechanics is that the information I have about the cat is consistent with those. So I have to say that the amplitude of probability of the cat is being alive and also being dead. So it is never saying the cat is alive and dead at the same time. That never says. This is the wrong way of many people to say these things. It's the information about the cat is in this way. And this has given rise to so many jokes that I've collected a few of them, and all the posters of the wanted Schrödinger cat dead and alive, or the doctor that says about your cat, Mrs. Schrödinger, I have good and bad news. You know, or there are all the jokes that you can imagine about the cat. And there is even at some point there was even a competition about jokes on the cat. I even like this one because it's related to physics, no? Institute for Quantum Physics, you are here and there and there and there and there. Okay. Of course, all this is not correct because you are not there and there and there. You would violate energy conservation. And now comes the rule that we were discussing about measurement. This is the postulate of quantum mechanics. So far, I've given everything in a very symbolic way. A dead and alive, up and down. But really, in quantum mechanics, you simply have a number in front, alpha and beta, which are, when you square them, the probabilities, when you measure, you will find this, and the beta square if you find down. So what the measurement says, it's a postulate. I cannot prove it. If you insist, I prove this, I cannot. Okay? Nobody can. Okay? There is nothing beyond the postulates in quantum mechanics. It says that given the wave function, which is the information you carry on your system, the connection to the real probabilities when you perform the experiments is this square rule. Okay. Amazing that it is a square, because probabilities are positive numbers, and this is the way you make it positive. But this is the way that additions of wave functions can have any sign, even complex numbers, can add and subtract before taking the square. So we don't know why, but in quantum mechanics, we have to accept that when we make a measurement, the result will not always be the same. There will be a probability of finding this and a probability of finding the other. That's it. So it's a genuine probability. It's not a probability due to mispreparation of wrong equipment. No, no, no. It's a genuine probability. Absolutely genuine. Now, just to be precise, the misuse of language is you know, it's everywhere. There is very little we can do. I mean, you know, who am I to change how the people write about this? In the center I am directing in Singapore, they already wrote a paper some years ago about that, complaining that journalists very often use the wrong wording. But it's an impossible thing because there are movies, there are people using that everywhere. So the wrong statements are the cat is alive and dead at the same time. No. The particle goes through the two slits. No. It can be here and there simultaneously. No. It would violate the energy conservation. No. I will give an example that this is not so difficult to understand. Imagine that, you know, I have a prediction for rain. Sorry, there's a misspell here. Tomorrow it may rain with a 15% probability. Okay, may rain or not rain. And then it rains. Okay, so the information collapsed. I had a 50%, it collapses. It rained, okay. But I never say that tomorrow it will rain and not rain at the same time. We never say that, okay? You say there is a probability of rain. So what is so easy with rain and classical probabilities, for some reason I never got it. People insist in misuse the language. Okay, now I will enter entanglement. So again, Jonathan, maybe this is the point to relax a little bit. No, I lost.
I was just making some comments in the chat. Sorry, it took a second to catch up with you there because you've just been discussing the fundamental postulate of quantum mechanics, the Born rule.
Yeah.
And I was just pointing out to people that actually some followers of the many worlds interpretation think it can actually be proven within that context. I think David Deutsch started that argument. I don't know if that's something you've come across. I was never entirely convinced by it myself, I have to admit.
Well, I think that this is, well, first interpretation means that there is no change in any prediction. Otherwise, it would be a different theory. So an interpretation means no change. It's just a way of understanding. And an interpretation is something your human brain makes. So many people may feel more comfortable by describing things with a given language, but the equations never change, okay? The proofs of the Born rule, the most serious efforts are not those of Deutsch, but those of all the school of Zurich that eventually goes back to John Archibald Wheeler. Sorry?
Oh, right. Sorry, I wasn't aware of that. Carry on.
Oh, yeah. So for many years, they have come up with a number of possibilities to deduce the Bohr rule. One is to relate it to a symmetry, and this is called N variance, N of entanglement, N variance. And there are papers related to why some states are selected, to the so-called quantum Darwinism and the pointer states. So there is the school of thought of more than 20 years to try to prove why the square is there, okay? Then there are other people that are called generalized probabilistic theories that have a different path to try to prove why the Bohr rule is there. So they are trying to substitute the rule by some principle, which might be deeper, okay?
Right.
All things considered, I think it's very nice that people do these things, but we still, I mean, we still work with this effective way of work, of going, okay? It would take me very far away to explain the efforts in the last 15 years to substitute the postulates of quantum mechanics. I think there is very nice work, but far from being a substitute for what we have, okay?
Yeah.
Yeah, and eventually it becomes very, very complicated, intellectually very, very complicated. Okay, so okay, so maybe move to entanglement. So there was a title in the talk, and finally we are getting there. Okay, entanglement. Okay, so it's all about more than one particle. That's it, nothing more. In a one sentence, entanglement is the consequence of the superposition principle when you have more than one particle. That's it. So to illustrate that, let me do it in the following way. I use the cat, okay? And I have two cats. So now my cat, my wave function, has to describe the two cats. And let me question whether there could be two cats, alive, alive, dead, and dead. Well, it's very trivial, no? I can prepare the two cats in the same box as Schrödinger did. I don't open the box. They are either alive, both of them, or dead and dead. That's so easy as that. Okay, so I can prepare that state, and perfectly decent. That's a quantum state. Instead of that, if you think of spins or excited electrons, we do that all the time in our labs. But this is not the same as two cats in two separate boxes, where one is alive and dead and the other is alive and dead. Okay, because if you multiply the two things, and here you see, then you have all the possibilities. The left is alive and the right is alive, but also the left is alive and the right is dead. You would have all the four possibilities. So you see the difference between the first line I wrote and the last line is that in the last line, they're independent. They have their own state. Whereas in the top line, I cannot write it as two separate individual states. Okay? When this happens, when the state cannot be written as the product of two states, this I call an entangled state. And this is entangled because they are correlated. If one is alive, the other is alive. If one is dead, the other is dead. They are correlated, and that's it. It's a correlation. And this is an immediate consequence of the superposition principle when you have many particles. Immediately you have entangled states. So the question is, to what extent these states are of relevance? This I will not enter. I think, Jonathan, you may have done that yesterday. You can prove that these states were necessary to do the Bell experiment, the experiments proposed by Bell and first done by Aspect and then by the people who got the Nobel Prize this year, that really discards, in one simple experiment, anything related to classical physics, all the hidden variable theories. were eliminated, almost eliminated, because there is always some little corner that you have to be careful with. So this is the idea. There is nothing but that. It's that the superposition principle allows for states which are very correlated. So whenever you measure, well, you may measure the two of them alive or the two of them dead with a 50% correlation. Now, if I only measure one, so imagine I open the box, but I don't look at it. I simply pick one of the cats. I close my eyes, I pick one of the cat, one of the two, and I see he's alive, automatically know that the other is alive without looking at it. So it's enough to look at one guy and decide that the other is either alive or dead, because I know that the correlation is this big. So that was what triggered the amazing amount of confusion in many, many relevant people, in particular in the Einstein, Podolsky, Rosen paper. And this idea of a spooky action at a distance. So again, this is wrong, okay? It's simply that it was a beginning and people were not clear about these things. But there is no action at all. There is nothing traveling from one to the other, simply that they are correlated, okay? There is no action at a distance. So you may think that you have a gigantic Schrödinger cat box that covers from here to Alpha Centauri, okay, 4 million years away, huge box. And you put the two cats and you wait for 1,000 years, and then you will open the box. And again, they may be alive, dead. Yet, the moment in the planet Earth, I open and I see a cat alive, I know instantaneously that the other is alive. But I never sent a signal. It's simply my information collapsed. That's it, nothing more than that. I cannot send any message with that. It never violates causality. There is no transaction of energy, simply that there is a correlation, okay? So entanglement, it's perfectly okay with all the fundamental postulates of causality and as measurement, everything. Now, we call entanglement, it should be a product, okay? When psi is not the product of two, okay? Let me say that essentially every state in nature is entangled. It's not the exception, it's the norm, okay? It's the standard thing. Technically, we also use another word, which is non-local correlations. Because you see, the two particles need not to be together. So these are no local correlations. And John Bell proposed an experiment to decide whether non-local correlations, okay, can be larger than any classical correlation. And indeed, it was measured by aspect. And this is the proof that this state I just wrote cannot be described by classical means. So this state I wrote, alive, plus dead, has a quality into the correlations, which is very strong and cannot be described by classical means, by what are called hidden variables. So entanglement is pushing the boundaries of classical physics. It's seeing that there are correlations that are inaccessible in the classical world. And the first and big question, can we use them? Can we now make new machines which are quantum machines that exploit entanglement? And the answer is yes, of course. The answer is yes. And then I will come to one of them here in the next section, okay? So let me just repeat once again. The fact that there are correlations is no spooky action at a distance, because that would be an action, that would be a causation, would be a cause producing an effect. And I insist, correlation is not causation, okay? It's not. And you have articles in internet under the title correlation is not causation. And this is one of the examples that many people put. As you can see, how many the ice cream sales along the year follow this curve. in North America, and the shark attacks follow the other curve, and they are perfectly correlated. But as you can imagine, they are not related, the sharks and the ice creams, okay? So it's not causing a shark attack, the fact that you eat an ice cream. Neither the other way around, that somebody attacks some shark attack is not producing you in Minnesota eating another ice cream, okay? So correlation is not causation. To be even more refined, causation is carried by particles, typically by light. And at maximum, it travels at the speed of light. So this is why there is no instantaneous action at a distance in nature. So causation needs the speed of light. Okay. So, and now I come back to the profound fact I told when the first question was asked by you. What makes quantum mechanics exceptional is not, it is the very fact that because we are forced to work with probabilities, you have to bookkeep probabilities. And it is given in a way that you add the wave functions and you only make contact with experiment with the square of the coefficients. And this is why now the wave function is complex, why if you are mathematicians, you have the representations of all the discrete groups, where you have a spin, when you have all the things come from that fact, okay? And why you have interference, why they cancel, why you see behaviors which are dramatically different from the quantum world. And the fact that we have to obey the Born rule, as we just discussed before with Jonathan, is a profound debate there. And I think that in centuries to come, we will go beyond that. We will have a better understanding of why we use the Born rule, okay? Again, if the world were classical and we would manipulate states, you should think that you only have probabilities. You don't have the square root of the probability. You don't have the amplitude. And therefore, you always have positive additions. You never have negative additions. The very sign of quantum mechanics is that you have subtraction in the wave. And that produces all the phenomena which are not accounted for in classical physics. No interference. Okay, so this is the entanglement piece. Jonathan, any comment?
No, keep going. Good for me.
Okay, so given that now we are familiar with all the things I said, why don't we go back to the fundamental line of thought that our progress is unstoppable, inexorable, and that we are just discovering quantum mechanics. So let me go back to that and magnify the 20th century. So everybody that looks back to the 20th century would tell you essentially about the wars and about the big disaster that humans have made and the political systems and but there is another narrative to the 20th century. And actually, let me bring two of them. On the top, you have the narrative of quantum mechanics. I told you, 1900, Planck postulates 26, entanglement 35, the first transistor exploiting our understanding of the theory of bands, the PhDs that Bohr directed in the Niels Bohr Institute, 47. Coherent light, that a laser is just the photons in the laser obey a single law, quantum law. GPS, why GPS is in the history of quantum? Because those are the atomic clocks that are orbiting the planet with a precision of 1 part in 10 to the 30th. Or the factorization theorem. If you have quantum logic, as I will show you now, you can do amazing things. I put www because it was made at CERN and it's for free. And this is why we are here without paying for the internet. Otherwise, we would be paying for it. So please defend the public sector in research. Okay, it's just for our good future. The quantum gates. 2005, we started to implement the first algorithms that used all the laws we have been describing to do computations. And in 2019, Google claimed the first quantum computer with quantum advantage. On the bottom line, even a more mysterious narrative. The first idea is computing is physics. So that's why our phone heats up, or why we need, we cannot have the computation done instantaneously. We need to follow steps, which are physical steps, and therefore have limits in the speed of light. This is Church, Post, and Turing, 1930s. The first machine that brings a computation, ENIAC, 46. And the first computation, by the way, that was useful was the census of the United States. So adding one by one without errors was the first computation done by a computer. The theorems of Shannon, we are using now the theorem of Shannon in this communication. We are using all what is the compression you can reach for a message. All that follows the theorems of Plot, Shannon, 1950s. The classification of problems, difficult and not difficult, NP versus P, 1970s. Neural networks, all the winters of artificial intelligence and springs in the 60s, 70s, 80s, 90s. Deep neural networks, the beginning of the 21st century. Advanced artificial intelligence, we are witnessing now all these open, chat, GPT, and all these ideas are the consequence of all these long things. Why I'm doing this? Because we are working now in the combination of the two things. We're trying to merge artificial intelligence with quantum computers, okay? So what you will see in the future is an amazing combination, okay? We have learned to learn, and now on top, we can substitute the substrate from biological substrate to electronic substrate, and finally to quantum substrate. And it's simply an amazing what we are starting to do. So it's inexorable, okay? We can use entanglement to make a quantum computer. And here's a little bit the logic. The logic, well, first let me show you that I'm not talking about the future. This is here. So I've chosen 4 little things. So on the left, you have those are individual ions. So each one is an atom, calcium atom. So we can play with them. We can put them where we want. This is an ion trap. We can illuminate them, we can read, we can change the state of every ion. Okay? This is one of the ways we do quantum computation. This is done by Manas Mukherjee at the Center for Quantum Technologies in Singapore. The right is the key element of a superconducting current qubit used for quantum computing, and this is called a Josephson junction. And it's a 200 nanometer structure. So we design them, we cut them, we deposit. It's made with aluminium, then we oxidize, then we put aluminium, we clean, and we make currents to go on superposition of clockwise and anti-clockwise. And we managed to do that. And we codified information in this element. On the bottom right, you have a cold gas. Here we take rubidium and we put it's a gas, it's not a trap ion, it's a gas floating. We make tweezers that pinch on each atom and we put it in the position we want. And then we can change the internal state of the atom. And as you see here, you may not realize that, but this is the Merlion, the imaginary animal that represents Singapore. Okay, I know it's not very clear. You don't know the Merlion, but this is a Merlion. And on the left, not only that, but we need to connect all these quantum devices. So this is our second satellite that it was orbiting the planet, and it was generating these entangled states there. This one, by the way, the name is called Spooky. Spooky 1, Spooky 2. And we call it. And Spooky 2 generated the first entangled pairs that were measured and the violations of Bell inequalities done in space. Why? Because now we are launching the third generation, which is called a spectral one. And it will take the same pair of photons and would send on the surface of the planet and will communicate continents through these entangled pairs. Okay. I think you will have a talk about using entanglement for quantum communication. Well, remember, if you go there, that this is the way we do it. This is called a nano cube satellite, and that's what we are doing. Well, I think it's a privilege to work in quantum mechanics. I mean, all these, like the privilege. You know, some people work to make some money and but some of us work for the amazing adventure of it. I mean, it's really a true privilege. So why we can use entanglement for computers? Well, as I said, in the 30s, we discovered that a 0 and a 1 is a logical information. Is a 0 is a logical 0, but in your computer, this logical 0 is a little magnet. So we use these things. In your computer, in your phone, you do that. Your memories, your RAM memories are done like that. But the minimum unit is of the order of 100,000 little magnets in your classical computers. Okay? So the question now is, what if we go to the single element, not to 100,000 to make your RAM memory per logical bit? Why? If we go to the one guy, if we use an ion to do a 0 and a 1, well, then the laws of physics change it because they are the quantum laws of physics. You may have superpositions. And then for the first time, you have a new concept. The superposition of two elements, and now thinking of them as logical zeros and ones, is the extension of the bit to a qubit, a quantum bit. Because now it's not always 0 or 1, but it can be in a superposition of 0 and 1, arbitrary superposition. And then all the actions that you do on it, you apply a magnetic field, you can rotate the spin. So these in logic correspond to rotate the 0 to 0 plus 1 or the 1 to 0 minus 1. And if you make them interact, you may control NOT gates, which are the fundamental gates for computing. So if we go down to the quantum world, every action is a gate. So the world is a computer. So just you need to tame it. Okay, it's just computing. It's doing things which are similar to computation, but you have to tame it to do the computation you want to do. So we have to tame nature to do our computations. But the logic we follow is different because now we have all these minus signs, all these superpositions, all these measurements, and writing any problem to be solved by evolution in quantum mechanics is not at all true. It's very, very good. What we know, and I'm sorry for this equation, is that if you have n particles and qubits, there are 2 to the n coefficients which are highly entangled. So n qubits carry 2 to the n superpositions. So in a way, a quantum computer is a massive machine with an amazing amount of memory. And then if you do a computation, this is called an action, a unitary action, it is done in parallel on none of them. So on top, nature is a massive parallel computer. So the promise is amazing. And this is why all the teams in the planet, we are working in doing this. I signed in the first transparency with my affiliations in Singapore, Abu Dhabi, and Kilimanjaro. And we are making quantum computers in Singapore. We are making quantum computers here in Abu Dhabi, and Kilimanjaro is making also quantum computers. So this is what is triggering all the effort nowadays. This is a quantum computer as it looks in superconducting currents. It's a beautiful machine. It's plated in gold. Okay. This is a fridge. It carries the temperature from the top to 170 our room temperature to the bottom at 10 millikelvin, so minus 273 degrees. And all the wiring are the radio frequency lines that have to go to the single actions that we modify. What is amazing is that we know that if we build this machine, we know exactly what algorithms we can run. And one of them is amazing, it's Shor's algorithm. And it will be able to factor large number in its prime factors. And why is this relevant? Because that the key element we use for cryptography. So whenever you connect to your bank account, whenever you use your social networks, whenever you send an email, all internet operations are protected by cybersecurity. You're right, in the old times, you could read HTTPS, the S meant security. And these protocols of cybersecurity, what they are trying to do is to protect your message from any hacker, okay, that would interfere. So you don't want to go to your bank and see no money there. So you want to be protected. So it turns out that all the algorithms we use are cracked by your quantum computer, will be cracked by a large enough quantum computer. So this is why we have news like this one, the National Security Agency in the States, which is the most powerful agency. It simply says we must act now against the quantum computing threat. It's so much at risk that for the first time in my life, everything is becoming proprietary and people don't want to have relations with certain countries, and there are exploitation bans for equipment, and there is a fight for talent among civilizations, which is very sad from my point of view, but it's a fact. Okay, it's a fact. It's happening. All this together, I just want to bring the idea of the singularity. I think many of you may be familiar with that, but this is my feeling. No, I use the words. I like the first quotation of Diderot. I'm admiring always the encyclopedia, no, very first account of knowledge, comprehensive account of knowledge in the 18th century. And he said this idea, if the union of thought and a machine is not possible, show this to me. It is possible. Tell me the consequences of the union, of this union. I think we are approaching the moment to discuss these things, because the advance of artificial intelligence that will be empowered on top by quantum computation, it's like telling us we should be discussing these things, okay? The word singularity, in my research, I detected the first use in the sentence by von Neumann in 1958. And he says the ever accelerating progress of technology and changes in the mode of human life give the appearance of approaching some essential singularity in the history of the race beyond which human affairs, as we know them, could not continue. And the more precise one is by Niels Bohr, okay, from Oxford. And in his book, Superintelligence, he makes the point that let an ultra-intelligent machine be defined as a machine that can far surpass all the intellectual activities of any man, however clever. Since the design of machine is one of these intellectual activities, an ultra-intelligent machine could design even better machines. There would be then unquestionably an intelligent explosion, and the intelligence of man would be left far behind. Thus, the first ultra-intelligent machine is the last invention that man need ever make, provided that the machine is docile enough to tell us how to keep it under control. So I think we are little by little approaching that, and it comes hand in hand in artificial intelligence and quantum computation. So this is my last transparency, and rather than a conclusion, I would like to open a number of discussions. By the way, this is our quantum computer here in Abu Dhabi. I took a picture myself. The first is that nature is sovereign, and it's unrelated to races, religions, or whatever. Nature decides. It is out there, all out there, simply waiting for us to drop our biases and begin to understand. Nature is patient. I love this idea that discovery is information that travels from the future to the present. Discovery, in the future, the information, it's simply coming to you. For quantum mechanics, my deep belief is that quantum mechanics is just an effective theory, which is valid in our present times. It tells us how to bookkeep probability amplitudes, but it does not attempt to bring a deep understanding of why everything is as it is. In particular, there are some of the questions which I think are beyond my understanding. Is there genuine quantum randomness? Okay, in this debate, Einstein would always say no. Bohr would say the famous sentence, God doesn't play dice in the atoms. Bohr's reply was, don't tell God what to do. No? So who are we? I mean, either there is or there isn't. If I had to be burned in a fire, I say my last word, I would say that as an old man that has been working in quantum mechanics all his life, I think there is something waiting for us, which is not wrong. Okay, so I'm on Einstein. So is determinism waiting for us at a deeper scale? In particular, what is this deeper scale? Is that the Planck scale, when gravity and quantum mechanics should merge? Okay, at the energies of the Big Bang. Okay, I have no idea. And string theory is completely useless to understand what happened. So is that the key element? Okay, is space-time no longer continuous? Variety, what is waiting for us? Yeah. So very likely, whatever is waiting for us at that energy would, I think, discard quantum mechanics as a fundamental description of nature. I think it's just an effective description. So, Jonathan, I think I'm done.
Thank you very much indeed. There's an awful lot of provoking thoughts there, and I'm sure there are a lot of people that want to come in on the discussion. Could I just ask if you could unshare your screen for a second so that then we can sort of get everybody. Yeah.
With pleasure.
I wanted to just ask one particular question, if I may, and I'm sorry if this sounds a little bit, I don't know what the right phrase is, provoking is the wrong word, but sort of needling slightly. It's not meant to be. We know with a quantum computer that a certain number of algorithms, Shor's algorithm being the archetypal example, is orders of magnitude faster way of factorizing prime numbers, as you say, than you could do with a, shall we say, conventional digital computer. But as far as I'm aware, there's no general proof that a quantum computer is going to be faster than a digital computer in all contexts.
Mm-hmm.
Firstly, am I right about that? And secondly,
Absolutely.
What is your feeling? Do you think quantum computers will outstrip digital ones in certain specific circumstances or just generally?
Yeah, it's a very good point. You are perfectly right. A quantum computer is not necessary to multiply two numbers. Okay. May I remind you that now when the astronauts fly in the space station, they carry pencils. You know that? No?
Yes. Yeah.
Okay.
Yeah.
So is the fact that people write letters with words meaning that you need them? No, you can write with a pencil. And in particular, there are some situations where the pencil is more advantageous than a word computer. No. So this idea that you always have to use the most advanced technology for anything, I think is simply wrong.
Yeah.
Do you need, for the youngsters, do they need to relate through the social networks or through Zoom? I think it's completely, my opinion, it's not good. I mean, they should meet in the discotheque or wherever. So the very fact that you have available the technology doesn't mean that it is the solution for everything. Exactly the same for this. Does a quantum computer provide an exponential advantage for factorization? Yes. Does it provide an exponential advantage for multiplication? No. So why should you use it for multiplication? You should, the opposite is true. You should use the best ingredient. As I said in the beginning, to make a brick, you need Newton laws. You don't need quantum mechanics. So this is the idea of what is the effective theory, the theory that properly describes all the relevant pieces of to solve a given problem. You always have to adapt to the correct intellectual equipment which is needed for that. And quantum computing has an advantage in factoring, and has an advantage in the so-called Grover algorithm, and very few others. Now, for those, it is good, and in some cases, extremely good. So the best solution would be to have traditional computers with a unit that, let me call it, instead of CPU, I would call it QPU, and would only be called on the spot of a given computation, but not as a general purpose computer. Even, that may be even more precise. We may have computers, quantum computers, which are not universal, but are specific for a task. And let me call them annealers or even simulators. You want to understand a new material or a new molecule. It may happen. People are working in this direction, and myself, I'm working in this direction to design a special purpose computer for that, for quantum chemistry or for finance or whatever. That's even more refined, you see. And this is the trend we see nowadays everywhere. So the high performance computing centers are now divided in machines. Some are neuromorphic machines, some are very highly connected machines, some will be quantum machines, and they may be talking to each other. Okay.
In some ways, I'm kind of reminded of the old analog computer days where you were designing a specific machine to do a specific job.
Absolutely, I agree. And we are doing that today, but people think we are not doing that. Many trades, many engineering problems are solved, and then you print a chip, an ASICs chip. And that is a special purpose computer, but people call it a chip. Your car has more than 300 of them, and they only do one task, but that task, they do it so fast, and that so little energy is used that it is the optimal solution. So we live in a world of adaptive solutions. So nothing new with the quantum, simply that it brings an amazing control, which is only useful in certain situations, but an amazing set of situations.
Yeah. There was just one more thing I wanted to discuss with you, if we could quickly, then we'll throw it open to everybody. We've used, and I think I used as well yesterday, we've used the term information a lot.
Mm-hmm.
What do we actually mean by that? Because we use the term entropy a lot in a variety of different contexts in physics. Mm-hmm. It's not at all clear, at least to me it isn't, that we mean the same thing or exactly the same thing in all of those different contexts. And I just wonder sometimes whether the same is a little bit true of information.
Yeah, may I, Jonathan, I think again, you go right away always to the hard question. I'm sorry momentarily to go a little bit technical. Okay, let me do it. 1 minute only. I don't want to get very technical, but imagine you have an entangled state 0, 0 plus 1, 1, and you are in England, you told me, and I'm in Abu Dhabi, okay? And we agree that tomorrow at 12, Universal Time, UTC, okay? Both of us will do the following. You will measure and write down my state, okay?
Yeah.
And at the same time, I will not measure and I will write my state. So it turns out that you will measure, you will find 0. So therefore you will write José Ignacio's state is 0, pure state. Whereas I don't know anything about your measurement. So I will find that I have half a probability of 0, half a probability of 1. It's the very same state, mine, at the very same time. What is the difference? That one has been written by you and the other by me. So that means that information is the description of a system by a given observer or person that has a given access. So information is related to who has it, okay? That's an essential element in quantum mechanics, and it is in general, no? But why we need to go through all the mess of information theory and reduced density matrices and all that? Because it depends on the person who is describing the system, okay? It's a little bit like relativity that depending what is your state, you describe differently the other people. It's the same, but for all the information of the system. And the very fact that it is attached to you is something that had skipped the mind of many people in the past. We thought that this was an absolute fact, but this is not so, okay? So,
Nice.
and then this is for quantum, no? But then I also think that if you now forget about the subtlety of the observer, the manipulation of information is really what all the artificial intelligence has excelled in the past. No? The very fact that many people thought that you would never reach the levels that humans have reached on particular tasks was on estimation of our process in the last 70 years of what is the learning, okay? Training, learning, have learned that we can use, you know, supervised learning, unsupervised learning, can use the environment to reinforce the learning, and all these things. And now we are using adversary neural networks fighting each other so that they train each other beyond whatever we know. And those ideas are simply one on top of the other, no? One on top of the other. Now the latest year is devoted to how to deal with very few data. So how comes that the human brain, with only seeing 3 things, 3 times the person knows a lot about that person? So all these ideas is amazing, and they are now big progress about that. So I think that all these ideas are under the name of information. And just to finish this comment, you know, I was very impressed by the papers in the 90s, the philosophical papers by Wheeler, by John Archibald Wheeler. I mentioned him before. He wrote a paper where he says that physics would be eventually information theoretical in origin. That's the sentence he used. I completely agree.
Bit from bit.
Bit, that's correct. I think it's amazingly profound. Okay, and I subscribe completely. I think it's a change. Myself, you know, I was training, let me say, bookkeeping quantum mechanics. No, you do the Schrodinger equation, you integrate like that, you apply these things. I never thought about these things till the late 90s. Then I started, and I may confess, I went through crises about everything. Just little by little, when the dust settled, that you start to finally understand that it was maybe simpler, but you needed to change dramatically your point of view.
James, you know, I'm conscious of the time. I'm sorry that I've chatted a bit too long. But let's throw it open to everybody.
And good conversation. Unfortunately, we are sort of reaching the end of the session. We are sort of going over time. Don't know if we would be able to open it to everyone, but we do have Sutra, so we are able to continue this discussion on our forum. I just had one clarifying question for you. So are you saying that in the sort of technological developments in the future, we would not have a quantum PC at home, but rather we would have maybe some sort of quantum encryption?
No, you don't need you don't have a supercomputer at home now. No? You have a phone. This phone turns out to relate with you with an algorithm, which may be OpenAI, ChatGPT, that has been trained in supercomputers. Mm-hmm. But you don't need to have this computer power at home. You simply need an interface to solve your problems. So I don't see why you should have a quantum computer at home. I don't see. I may be completely wrong, and I don't know. But I don't see why. In the next 30 years, for sure, you will not have them.
Great. Well, I guess we'll see how it goes. Well, thank you so much, Jose, for.
Well, next time you guys come by Abu Dhabi or Singapore, call me and you.
We will for
the
sure.
Real thing.
Well, I need to see that beautiful machine. It really is. It's really pretty, even just to look at.
It is. There is an element of poetry when you work there.
Yeah,
it's so beautiful, man. It's you have the feeling, and everybody there working, you are doing it better and better and beautiful, because we all think that there is an element of aesthetics in our work. Yeah. So,
yeah. Great. Yeah. So thank you so much for this presentation.
I'm sorry that I obviously talked too much. But,
no. What you said was really interesting. I just wish we could listen to you more.
No.
But yeah, thank you so much for today, and thank you for looking into, well, for your work together with your presentation. And thank you, of course, Jonathan, for engaging.
Well, thank you, Jonathan, a lot.
Discussing with us.
It's a pleasure to have you there. Yeah, a real pleasure.
And of course,
thank you very much. My pleasure being here.
And of course, thank you to everyone here in the audience for listening in and of course contributing in the chat. Just before we all go, I just wanted to remind you all, I mentioned it earlier, Sutra, our online forum to keep this conversation going throughout the week. Until next week, of course, where we will be joined again. We have Bohmians next week. On Saturday, we will have Emily Adlam talking again about entanglement with her presentation entitled Spooky Action at a Temporal Distance. And on Sunday, we will have Professor Basil Hiley, who we've heard a little bit from yesterday, with his presentation entitled My Entanglement with Entanglement. If you do want to contact us, you can use our website or email address. Eleanor@paricenter.com is the best place to email to. But until then, thank you again so much. Thank you again, Jose, Jonathan, and everyone here. We'll see you again soon.
Thank you, everybody.
Pari Center. Bye-bye.
Bye-bye.